Okay, we're entering a slightly different phase of our physics here. We're trying to sort of understand how some of these concepts of voltage and potential and field and force and those sorts of things apply to actual inventions, or I should say how inventions came from some of these concepts or utilize some of these concepts. So capacitance is a kind of a fancy word, but that's the title of our next chapter. And what we're trying to do is kind of capture the idea of field and use it, and what devices use electric fields. And one of the most common devices, one of the simplest devices, is what we call a capacitor. A capacitor. So you've probably heard of this device before. Okay, and the way a capacitor is designed is usually they'll take two metal plates like this, and they are both flat. Not always, but oftentimes they'll take two flat plates and they'll put opposite charges on each one. So one will be positively charged, the other will be negatively charged. And because it's a conducting surface, the charges will naturally spread out in a uniform manner to get away from each other. And let's forget the whole idea of fringing. Let's pretend these are infinite. In other words, fringing is when the E field sort of bends around the sides. Let's just pretend that this sets up a nice uniform electric field from the positive plate to the negative plate. Okay? All right, so a couple things happen. We have this E field that's set up here in the green, and then this is the hard part to understand. You have basically two equipotential surfaces. They're physical surfaces. These are actual metal plates, and so the voltage on each one is a constant. So the voltage is constant, or the potential is constant, and that's true for both plates individually. Okay, that's true for them both individually. And generally we make them equal and opposite. And this is usually done using a battery, actually, or some kind of a power supply. So oftentimes you will notice that this is attached to the positive end of a battery. And then the other plate is attached to the negative end of the battery. Okay? And that's how you could supply yourself with a positive on each. Now you might say, how can you have a positive voltage? What are you talking about, a positive voltage? Positive voltage here just means positive with relation to the edge of our universe. Okay, so let's say that this right here is 3 volts. What do we mean by 3 volts? We mean that if you compare this to V equals 0, which is way out past the edges of the universe, if you compare the amount of potential on this plate to the amount of potential out at the infinite realm, there's a 3 volt difference. That's what that means. And then the other plate might be at negative 3 volts, which means that it's 3 volts lower than the edge of the universe. I'm saying the edge of the universe. I'm treating the universe as infinitely large. But let's say the universe is not infinitely large. I'm just saying if you go way out to infinity, you find V equals 0. So this is the top plate is 3 higher than infinity far away, and then the lower plate is 3 lower than infinity far away. So this would be called a 6-volt battery, right? So the battery actually is not a capacitor. The battery is an electrochemical device that permanently separates charges. There's a special situation going on with the chemistry inside a battery, and they are pre-created to have a voltage difference. And they discharge very, very, very slowly, actually. So batteries are designed to sort of trickle a charge, trickle its electrons through a circuit and into its other terminal. So slowly but surely, the electrons will make their way through this wire, through the circuit, and then back into the positive side, and slowly the battery will become useless as it begins to neutralize. Now, technically, this is an open circuit, though. Like, there is no circuit here. you guys understand that a circuit is only closed when they have physical contact. So technically, right now, in theory, this battery should basically keep the two plates charged forever. Okay? Now, if you push the plates together, that's called shorting the battery. And the electrons will flow very quickly through the circuit, and basically the potential difference inside that battery will eventually not exist. So how do you kill a battery easily? How do you totally ruin your nice lithium battery? You take a wire and you connect it like this, and you wait a few seconds, and then the battery has 0 volts. So don't do that. That's a dumb thing to do. You're wasting the battery. And so when you lay all your batteries in a drawer, right, you take all your batteries, you throw them in a drawer, they bump into each other and stuff, you might actually short a few. Probably not. It's kind of hard to touch both ends. And now you can see why they definitely keep the two ends of the battery very far apart from each other. But if you're working inside of a car, right, car batteries, in my opinion, are kind of poorly designed, because your positive terminal and your negative terminal are right stinking next to each other. You know what I mean? All it takes is for you to, maybe you're holding like a piece of metal, like a metal rod in your hand, and you're using it for something, and then you set it down by accident on top of that battery. It's going to spark and arc and short that battery, and that battery is going to be worthless. All 12 volts wasted in just probably under a minute, under a few seconds. So it just depletes the whole battery. So never short your battery if you can help it. Sometimes you'll notice my car battery isn't starting the car anymore. It could be not the only possible reason, but it could be that somehow the wires that come out of the positive end and the negative end, they both go to different parts of the car, but maybe at some point something broke free, and this was screwed into something, but it broke free, and it wiggled its way over, and it touched another wire that was touching the positive side, and then a few sparks happened, and then your battery's not holding it. It's not charged anymore. And you're like, what happened? Did I leave my lights on? Not necessarily. Maybe some contact was made and shorted out the battery. And then there's much more to a car, actually. Sometimes batteries have charge, but they don't recharge. That's another issue. Okay, but we're not talking about batteries today, because those are slow voltage sources. What we're doing here is we're taking two plates and we're creating a very quick discharge source. So the capacitor's job in a circuit is to provide a place in the circuit where energy can be very rapidly given away. So if a battery is a long time draining, capacitors can be instantly drained. So batteries will discharge slowly, capacitors will discharge quickly. All right, and now, what are some of the equations that kind of govern this? That kind of govern this situation? Okay, so first we need a new quantity. It's a question of how much field can be saved in a capacitor, like how much voltage can be stored in a capacitor. Now you might imagine that would actually depend on how many field lines we can create. How many green lines can we create? Well, that depends on how big the plates are, right? So think solar power, right? Why isn't solar power powering everything in our universe right now? Like, how come we don't use solar power to power our photocopiers downstairs? Or why don't we use solar power to, run all the computers in the Orange Unified School District? Maybe it's because the solar companies charge too much. Just building the solar technology to each building is too much. But also think about it. Solar panels are only as useful as they are big. This is a real problem with solar power, you guys. The government obviously wants to cut down on fossil fuels and are looking for alternative energy sources. Why not just steal energy from the sun? I mean, gosh, is there a bigger source of energy in town? No. But why can't we just steal all his energy, or for that matter, enough to help us? The reason is area. You got to have a huge plate even to get much going at all electrically. A huge plate. Cars would have to be covered in solar panels. And that might not even charge the battery when it's sitting still. There's so many reasons why solar is kind of a joke. I always thought it'd be cool if, and this is just me talking, capacitors are similar. If you want to store a large amount of charge, a large amount of field, a large amount of voltage, you need big plates. So sometimes you'll notice that capacitors aren't even shaped the way you would think. If you see a capacitor in a store that looks like this, if you see a 5 microfarad capacitor sitting in the store like that, you can probably be sure that if you cut this thing open, there's 2 plates inside. Much like the drawing I have above, probably actually congruent plates. So Mr. Short probably should have drawn that a little better. So it's all enclosed in a piece of ceramic. Actually, it's kind of dipped in ceramic, like an ice cream, like a dipped ice cream cone. But actually, the 2 plates are in there, and 1 wire to each plate. Okay. You might say, what the heck is the ceramic for? The ceramic is there actually to make the field stronger. We'll talk about dielectrics a little bit later. So these are often like 2 plates, each with a wire, wire, plate, wire, plate. Take it like you dip an ice cream cone in chocolate, right? And you dip it in ceramic and it creates like a shell around it and between it. This way no one can touch the plates. And also if it's the right kind of ceramic or the right kind of material, it could actually increase the strength of that capacitor, the ability for it to store energy. Okay, that's one way to do it, but really it's all about area. It's really about area. If you want more capacitance, you need more area. So sometimes you'll notice they have these capacitors in the store that look like this. Very different looking. Okay? So the idea is if more area produces more field and ultimately more of a discharge, why not take the plates and wrap them around each other in a spiral fashion? So if you cut this open like this, you'll notice something. The plates are actually wrapped around in a spiral like this. So there's a wire connected to a plate that's wrapped around. So it's kind of like this, like a jelly roll. And then between that is the other plate. So it's 2 sheets. Imagine taking 2 sheets like this, 1, 2, and then rolling them up. Can't draw this very well, but feels like I'm drawing a half pipe. I've done that many times. So you're kind of rolling the sheets together. This is the limitations of my art skills here. I'm quickly running out of artistic ability here. Hold on. I think I got it. Okay, so you wrap them around each other, but you got to keep them separate. You cannot let them touch, or you'll get instant discharge all the time. Like, it'll close the circuit. So you wrap them around and around and around using a machine. You keep them at a slight, probably a constant distance apart from each other. And from top view down, you get something like this. I can't draw it. It's got to be equidistant throughout the whole journey there. And then one of them's connected to one wire and one of them's connected to another wire. And now you got a lot of area there, all in a very tight space. Just a matter of convention, just so you guys know, there's 2 words that get used quite often that are kind of misnomers. One is we will call, let's say that this plate is charged with positive Q, and this plate is charged with negative Q. We often call this this is a horrible way to say it, but listen, we will often say that the charge on the capacitor is Q. This is actually a really bad misnomer, meaning it's a poor use of words, because actually the charge on the capacitor is 0, and it's capital letter C, and it's always equal Q over V. It looks like an ice cream cone. You know how ice cream cones look like this? Doesn't an ice cream cone kind of look like this? And this Q over V kind of looks like an ice cream cone. I kid you not, that's how I remembered it in college. Q over V looks like an ice cream cone. It looks like you're about to put an ice cream ball into an ice cream cone. Okay, stupid, right? But there's a lot of equations coming our way, so we need ways to remember it. So capacitance is an ice cream cone. All right, and honestly, it's not a complicated equation. You could write it this way and say, you could say that charge is directly proportional to, oops, spelled proportional wrong. Oh, no, I didn't. That was correct. Charge is directly proportional to voltage. Okay? Charge is directly proportional to voltage. And what is the constant of proportionality? Okay, here's what I'm saying. Let's say you take a 5-volt battery. You hook it up to a capacitor. And you find, lo and behold, you have stored 0.02 coulombs. Well, it turns out that C is 0.004. 0.004 is our constant of proportionality. It converts volts to actual coulombs, you see? So it's just a number, but it does kind of indicate how good the capacitor is, because you might have a slightly different capacitor that you bought at a better website, and you put 5 volts on that thing, and you get 0.3 coulombs of charge stored. So now you divide this. Let's make something more convenient. How about 0.35? You apply the same battery to a brand new capacitor you bought on a better website. Maybe you spent $1 on this capacitor instead of 20 cents. And you get 0.07. Obviously, this second capacitor can store more coulombs for each volt applied. This one can basically store 0.004 coulombs every time you apply a volt. This one, the second one, can store 0.07 coulombs for every 1 volt you apply. So you can get the feeling that C here, it's just a proportionality constant, but the bigger C, the more coulombs of charge we can collect per volt we choose to apply. So you might say, why is one better than the other? Well, one's probably a parallel plate capacitor. The other one's probably a cylindrical capacitor. Cylindrical capacitor is going to be able to hold a higher Q on its plates, even though you apply the same 5-volt battery. Okay, so as you know, the first guy who kind of makes breakthroughs in these gets the name on the unit. So a coulomb per volt is often referred to as a farad, a capital F. Okay? And not always, but usually if you look on a capacitor, you will see some numbers. That is a reference to how many farads that capacitor represents, or maybe it's how many microfarads. You kind of have to be in the actual field of electronics to distinguish that. You know what I mean? You might pick up a capacitor at the store and it says on there, 5. And you're like, dude, a 5 farad capacitor, I can store 5 coulombs of charge if I apply a volt. Probably not, actually. 5 coulombs of charge is a lot of charge. Okay? That is a lot of electrons. Remember, each one's only 1.6 times 10 to the minus 19th. Yeah? So it's probably not a 5 farad. It's probably a 5 microfarad, or maybe even a 5 millifarad or whatever. I don't know. 5 picofarad. Who knows? My point is, don't judge by the numbers, but some capacitors you will actually see, the capital letter F on there, or micro F or whatever, and then you'll know, oh, I know what that is, and then you can do a direct conversion. Otherwise, you got to go to the front of the store or go on the website and ask a question like, does 5 mean 5 farads or 5 microfarads? You just kind of prove yourself dumb for a minute until you learn the lingo of the electronics engineers. The electronics guys, they know. But not everybody knows. Why would you know? Why would I know? I'm not an electronics buff. Okay, so coulombs per volt. That's a farad. By the way, we almost never have 1 farad. To have 1 coulomb of charge collected after only applying a volt, man, that would be a serious amount of coulombs to get from a single 1 volt battery. It would mean you have a very, very, very efficient capacitor. I'm not even sure it exists in the universe. Okay? So just be aware of that. Now, capacitors actually occur in nature. They occur in nature. And our book mentions a couple of examples of that. The Earth itself is a capacitor. Did you know this? The Earth itself is a capacitor. It's a spherical capacitor with 2 plates. The atmosphere can store charges that the Earth doesn't have. In other words, there can be a net difference in charge between the surface of the Earth and the surface of our atmosphere. Think about it. That's how lightning happens, isn't it? A sudden discharge from one plate to the other. Why would lightning travel from one plate to the other? By the way, some people say it travels from the bottom up. Some people say it travels from the top down. I think that's a matter of convention, right? Do you want to talk about electrons flowing, or do you want to talk about protons flowing? You know what I'm saying? So I'm not too familiar with the phenomenon of lightning, but lightning is definitely a temporary capacitor discharging. That's what's happening. And it's the atmosphere versus the Earth discharging there. Or maybe it's the atmosphere versus your head, and you get zapped with lightning because your head's the biggest voltage difference in town. So the lightning chooses to hit your head. But the lightning is the discharge of the energy there. Okay. Also, if you've ever skied at night, you can actually get sparking going on between the snow and your skis, or actually it might be between your ski tips. I'm not sure, but our book does mention night skiers sometimes seeing sparks, and that's because you have temporary discharge there. Okay, so anything could be a capacitor, but we design them on purpose for the purpose of electronics. Okay, our book does mention that when a capacitor is charged up, so let's say you have a capacitor, maybe it's a parallel plate capacitor, so now you kind of know what's inside this ceramic disc. If you hook this thing up to a battery and then you disconnect the battery, what you've done is you've made this thing into a battery. Okay, so you take the wires, you hook them up to a battery, right? Then you remove the battery. Well, guess what? You still have a battery. This is now your battery. The difference is the capacitor will discharge its charge very quickly. I mentioned that earlier. Now, in this class, we're going to assume that if you just leave the capacitor like this, it will stay charged forever. So obviously that's not true. There's nothing in nature that lasts forever, but there are some other effects going on. Energy is being stolen. I'm sure that the energy is not going to maintain a constant value, but let's just, for theoretical purposes, assume that that capacitor, if charged up to 1 volt, will remain at 1 volt forever. Now, what happens when you touch it? What happens when you touch a 1 volt capacitor? Is that scary? I mean, is that a frightening thing, or is that like a no big deal? Because I know what happens when I touch a 5 volt battery, nothing. Or even a 12 volt battery. You could feel it going through your body, but it's not going to kill you. It might. I wouldn't suggest doing it, but I've touched wall sockets by accident in my home, and I mean it's disturbing. But what about a 1 volt capacitor? Are we scared of those? Okay, the 1 volt won't kill you, but the capacitor might. And the reason is current is what hurts. The flow of the electrons through your body, right? And current is a separate phenomenon we haven't studied quite yet, and it represents coulombs per second, also known as an ampere, okay? An ampere, or amperage, if you want to call it by its adjective form, okay? High amperage can kill you. Well, what causes high amperages? Voltages do, but there's another factor. If the top is just 1, that's not a big deal. But listen, if it discharges in a very short time, let's say 0.0001 seconds, 1/10,000th of a second, that's 10,000 amps. You understand? The highest amperage in your home is 15 or 20. You understand? So a 1 volt capacitor isn't dangerous because it's 1 volt. It's dangerous because it discharges almost instantly. Right? In other words, you have a very high amperage in that situation. And so a 1 volt capacitor can easily throw you across the room. And if that doesn't kill you, if the shock doesn't kill you, then hitting your head on the wall on the other side of the room might. You understand? Be careful with capacitors, especially the big looking ones. Okay. So if you are looking at a circuit diagram and you see something like this, guess what? That's a capacitor. It might be a parallel plate capacitor or it might be a cylindrical capacitor. This is just the universal symbol for capacitor. It looks like two parallel plates. If you see a symbol that looks like this is a battery. Okay? It almost looks like two capacitors. But you can see their symbols are quite similar because actually they're really not that different. They're both voltage sources.